Okay, so the first thing that we found with the relativistic treatment, the first difference that we found with the classical non-relativistic treatment is that the final velocity of the clump of particles, okay, is actually greater than 1/2 the velocity of the initial incoming particle, and it's greater by an amount which depends on gamma. Now, basically, I in the previous part of the lecture, I indicated that this fraction, in order for this to be true, then this fraction has to be greater than 1/2 for gamma is greater than 1. And in order to see, that may not be obvious, but in order to see that, if we invert this, we get gamma plus 1 over gamma, which is equal to 1 plus 1 over gamma. And this now has to be less than 2. Okay? Has to be less than 2. And what we see is that when gamma is greater than 1, then this second term is smaller than 1, and indeed this is going to be always less than 2. Okay, so that's the first interesting result. Okay, now what about the mass? Is the mass conserved in the relativistic treatment? Well, in order to answer that, we should remember that the magnitude of a 4 vector is invariant, and in particular for the 4 momentum, which is a 4 vector, we have that E over c squared minus the p squared, where p is the 3 momentum, the magnitude of the 3 momentum, is invariant. Okay, and furthermore, since the total 4 momentum, the total initial 4 momentum, and the total final 4 momentum are both 4 vectors, okay, then their energy, momentum, and variance are equal. Okay, so we basically are using some basic properties of 4 vectors here. Okay, and so then if you actually plug in here for what the magnitudes of the 4 momenta are, so what we have is that gamma plus 1 mc squared minus gamma mv squared. This is sum over I, let's call it P0. This is the temporal component of the 4 momentum initially squared, and this is the spatial, the 3 momentum squared initially. Okay, then this is equal to gamma prime m prime c squared. Okay, that's the temporal component squared, minus gamma prime m prime v prime squared. Okay, I didn't like the notation that I'd done before, so here I tried to make it more clear. This term is the total energy of the 2 particles before the collision. Here is the total 3 momentum of the 2 particles before the collision. Here is the total final energy of the clump after the collision, and the total 3 momentum of the clump after the collision. Okay, now since both sides of this equation are invariant under Lorentz transforms, that is, their values, the value should not change when we transform from one reference frame to another, we can do a little trick here, and we can transform the right hand side of the equation into the rest frame of the clump, in which case gamma prime is equal to 1 and v prime is equal to 0. Okay, so that term basically is going to go away, and that's going to go to 1. So what that leaves us is just doing the math.